Hi everyone. So VSURF stands for Variable Selection using Random Forest. And I present you a joint work with Jean-Michel Poggi and Christine Tulomalo. So the Random Forest was introduced by Bryman in 2001. So it's a very efficient algorithm in statistical learning, and you can deal with the classification or regression problem. So just to fix the notation, I have a learning set Lm. So these are ID observations of x, y vector. My x are my inputs. They are in RP, and the y's are the output. So if your output set is R, it's a regression problem. And in this talk, I will only focus on the classification problem where the outputs are categorical variables, and I denote by L the number of categories. So the goal in statistical learning is to build a predictor H hat, which is able to predict any new input and give us the corresponding outputs. And especially in this talk, I will also focus on the selection variable problem. So a little bit of details about random forests. Random forests are an aggregation of randomized trees. So each tree H at theta L depends on the independent adding additional randomness theta. And once you build all the trees, you aggregate the trees by taking a majority vote. So each tree gives you a class, here class C, between 1 and L, and you just take the majority class to predict the final output. So what is classification tree? You have an example on the right. So the principle is to recursively partition the input space. So at the beginning, you get all your data in the root node, and then you try to split in the best way as possible into two child nodes by splits which are looking like this. So one variable, input variable, less than a threshold. If this is true, observation goes to the left, and if it's false, observation goes to the right. And when you are looking for the best split, the idea is that you want that the heterogeneity measure associated to y is low in both child nodes. So in classifications, you have some Gini index, for example, to you want to minimize the heterogeneity in at each step. And one famous example of those trees are the card trees, introduced by Bryman and co-authors in late in the 80s. And the main idea of card is to perform two steps. The first step is to build the maximal tree in the sense that any node cannot be split anymore because all y's are of the same class. And once you get the maximal tree, you have a second step to prune this usually over-fitting tree to get the best tree with the best prediction capacity. So this was for a tree, and then the most famous random forest algorithm in the literature is the random forest random inputs. So the idea is that you start with your learning set, and you build a Q bootstrap sample from it by drawing n observation among the n observation of the learning set with replacement. And once you, on each bootstrap sample, then you you built a random input tree, which gives you doubly randomized trees. So the first randomness gets from the bootstrap step. And then the random input tree is actually a variant of cart where you get an additional randomness theta prime. And once you get all the trees, you aggregate them. And in practice, and we have also some results, this additional randomness and the aggregation gives you an increase of efficiency. And most specifically for the random input tree, the variance is the following. At each node, in a card tree, you seek for the best split among all the available input variables, whereas in a random input tree, you first select m-try variables at random without replacement, and then you optimize your split only with these selected variables. And the second difference with cart is that an RI tree is not pruned. So you keep the maximal tree for all the trees in the forest. And just I insist, the m-try parameter is the most important parameter of random forest. And it goes from 1, which in this case, the splitting variables is completely random. And the extreme other case is m-try equals p, where you retrieve the classical cart tree, and this reduced to the bagging method also proposed by Bryman earlier. So the main R package that implements random forest, so there are several, and the reference package is random forest, ported in R by Yo and Wiener, and based on the code of Bryman and Cutler. And quite recently, we have some other implementations in R. So first, the Ranger package, which is tailored for high-dimensional data. So that was the wide data of Benoit earlier. And Herborist, which is tailored for big data when you have a lot of observations. And so the two main parameters in this package, so here you have the names of the parameters in random forest, Ranger, and Herborist. And they hopefully have the same default values. And so the idea is that we will see the benefits or not to include those new implementations in the VSURF, which is a variable selection technique, which is based on the variable importance. So the variable importance is defined as follows. So once you build your random forest, associated to each bootstrap sample, you have an out-of-bag sample, which are all observations that were not selected in the bootstrap. And now we will use those to compute the effect, to measure the effect of permuting the values of a variable j in those OOB samples. So you fix j, your variable, an integer between 1 and p, and then for each out-of-bag sample, you randomly permute the values of the JS column, the variable's values. And then you compute the mean error of a tree before and after those permutations. So, and the variable importance of xj is defined by the mean increase of tree error caused by this permutation, and hence the more the error increases, the more important is the variable. VSURF wants to reach two different objectives of variable selection. So the first objective that we call interpretation is that if you want to select all important variables in your data set, even if they are quite redundant with each other. And the second that we call the prediction objective. If you want to just select a very few subset of variables, which will give you a good prediction, still good prediction. And we want to build an automatic procedure which fulfills these objectives. So this is a standard output of VSURF on a simulated data set. So I have two class supervised classification problems, 100 observation and 200 variables, and 6 variables who are effectively linked to Y. And just to, I don't go into lots of details about the procedure, but when I perform the VSURF function by default, it starts by computing 50 random forests with a variable importance computation to get the VI mean and VI standard deviation on the first top graphs. And then we have a threshold here in red to get, in this example, 31 variables selected. And then we compute nested models by adding variables in the decreasing order of variable importance in the model to get this graph. So we compute again a certain number of random forests. And finally, the last step, we want to eliminate the redundant variables in the previous selected set. And again, we compute again lots of random forests at the end. So the previous graph was obtained with the following code, standard code. And here you have a measure of the computation time. So it takes around 1 minute. And now my first reflex to see what will give a ranger in those situations was to replace all the calls to random forests with ranger, and it gives me this result. So let's say approximately the same overall computational time. So I have an extra parameter RF implant to RF implementation here. And actually, Arborist, I have several issues, so it's not fully implemented yet. And actually, when I tried this exact same code a few months ago with the ranger implementations, it was twice slower than random forest. So I think the ranger team is continuously improving their implementations, but I was still quite surprised because ranger should be, let's say, faster than random forest in those cases. And so just to understand what's going on, I only look at computation times of a random forest. On the left, when no variable importance is computed, and on the right, when VI is computed. And the main message is that, as you see for ranger, when you ask for variable importance computation, the computational time rise significantly, whereas random forest is quite stable, and actually arborists do not give you the possibility to get this. And just in the more high-dimensional case, where I have 2,000 variables, this is even more striking. If you do not ask for variable importance, ranger is really faster than random forest, but as soon as you ask for VI, it becomes comparable. And in the big data context, Arborist is actually, faster in this context, but you can't compute variable importance easily. So just to conclude, I try the two implementations in real data set, so one high-dimensional one. In this case, actually, ranger is slower than random forest. And in a spam data, which were used in the first talk of this session. Also, Ranger is slower. So I have still some work to do to speed up VSURF, and the main message is that it's not so simple because I compute a lot of random forest models in the selection, in the procedure. Some of them are using variable importance, so if the package do not speed variable importance, it's no help for me. And actually, all the embedded random forest models, it's kind of struggle also with VSURF and also Herborist. And that's it. Thank you.
Thank you, Robin. We have time for quick questions.
Thank you. First, I'll say I used your package in my work, and I really liked your implementation. So thank you in general.
Thanks.
I was surprised and saddened by what you showed. So I have two follow-up questions. The first one is, I imagine you contacted Ranger. Did they respond and said, "Oh my God, we didn't know that we were that slow, and they're going to fix it"? Or
No, I'm in no contact with them, but it's quite recent work. But
okay,
sure.
So that was the first question. The second is, I understand that there are alternative ways of trying to do variable importance that maybe don't require the out-of-bag samples. So
yes.
Do you imagine that using one of these, even though it would be more biased, might be a way to leverage? Because for large data sets, it's just not usable. So having it faster is important, actually.
Yes, you are right. They call it the MDI, so mean decrease impurity variable measure. Mm-hmm. And effectively, this measure is directly included in all packages, so you don't have to do extra computations. And actually, we didn't use this because in the literature we saw maybe more bias in some of the situations, and let's say all the drawbacks that were associated to this measure were not with the MDA, so mean decrease accuracy measure that we use. And moreover, since we always compute several random forests and then take the mean, we have, let's say, less and less drawback in this framework. So it will obviously be faster, but maybe the result...
You don't trust the results enough.
Yeah.
Okay, thank you very much for your work again.
Okay, thanks. One last question.
Thank you, and thanks for the talk. Very interesting stuff. I've used random forests in such a way to determine variable importance in my work in a more ad hoc way. And I've also used GBM variable importance, and I wonder, could you comment on whether you see the two as being roughly an equivalent approach, as in the variable importances, say, given by a GBM, would they be just as useful or as valid as the variable importances given by a random forest? Thanks.
Yeah, so actually, I don't really know how the variable importance is computed in GBM, so but maybe we can discuss that. And but let's say that the variable importance computed by the random forest was a lot studied, and I have, as I said earlier, a good trust in their results, and so that's why we use this. Yes.
Okay, thank you very much, Robin.